compromise between a direct mapped cache and a fully associative cache is a so-called n-way associative cache. What we do is to take all the cache rows and divide them into a number of cached sets. Each set has n rows. And n is, for instance, 2, 4, or 8. So what we do then is to first decide which set, and we do that using the address, just as we did for a direct mapped cache, but now we decide, we determine which set we should use and not exactly which row. Okay, then when we have found the set, we loop through in the C code, not in hardware. Then we do all comparisons concurrently and we check if we have the data that we are looking for. And if we have only one set, then we have a fully associative cache. And instead, if n, the number of cache rows in each set is 1, then we have a direct mapped cache. When we get a cache miss, we have transferred only one word between cache and memory. But it's much better to transfer a number of words, such as 8, 16, or 32. For instance, the power machine that we have, it has, when there is a cache miss, it transfers 128 bytes at a time. Okay, so, but if we instead assume that we have, let's say first that a word is 4 bytes, so we can store an int and an instruction in a word. Okay, so when we get the cache miss when we fetch an instruction, we instead not only fetch 1 but 8 instructions at the same time. Okay, so what we do then is to avoid 7 cache misses that would occur if we didn't fetch all 8 words, and if we actually will use all the 8 words and not only the first, for instance. So what we should do now is to view memory not as an array of, let's draw it here, not as an array of words like that, but instead as an array of blocks. So each block is a little bit bigger. 128 bytes, for instance. Okay, so what we do now is that we introduce a new parameter to the cache, and that is often called the block size. And when we use the cache or access the cache, we first want to find which block number it is. So what we are looking for is one of these. So this is block number 0, number 1, number 2, etc. Okay, so what we do is to take the address and divide it by the block size. Okay, how is that done in hardware? Say we have a number of bits in the address, and we can say, just for illustration, that the block size is 16. That's quite a little, but we can say that anyway. Then we in the source code we divide by the block size, and an option is instead to shift 4 steps if the block size is 16. What that means is that we will remove these bits and just look at this. But what we can do in hardware is simply to just use these bits and ignore those. But of course we will need them when we actually fetch the data. I mean, this is the block number. And this is a byte in the block. Okay. Although it's a byte in the block, so far we have only simplified this and used data that is an int, but the principle is the same. So what will we use this for? Well, we will use it for fetching exactly which bytes within the block. So what we have in the cache now is 16 bytes. I mean, if we use this block size of 4. No, not 4, but of 16, since we shifted 4. Okay, so we have some from 0 to 15. And what we have done is, now we do the following: that we first find which block number it is. We do that by taking the address and divide by the block size. Okay, and that is the same thing as just looking at these bits in the address. Okay, now we should find out which set is this block possibly located in. And we do that by taking the block number and use that some bits in the block number, for instance, these bits, as the index into the cache array. So this will be the I used here. Okay, and then there are n cache blocks in this part, and we go through all of them and check if the block number stored there is the same as the block number that we were looking for. We cannot use the exact address now. Look here, we had as follows before, that we compare the addresses. But that is not what we store in the cache, since we need to store the it can be if we an address, as in this sense, it could be to any byte within a cache block, but that is not what we are looking for, since we are looking for the cache block. Okay, so therefore it is this number that we store in the address field of the cache. Okay, so we check that it is the cache block that we find, that we are looking for, and then we take, we want to know which byte in this block that we should use. Okay, so now we use the block size, and it will be, we take these bits, so these bits will be the K. Oh, okay, so we select some data here and read that from this entry in the cache. Okay, so how big is the reasonable block size? One word is too small, or 4 bytes. 32, that's quite a little. 64 and 128, that's common. But what about having like 1024? We cannot say that that's a bad idea or that it's a good idea. It depends on the application. If the application uses a lot of data that is consecutive in memory, then it might be a good idea. But usually it's too much. It's better to have a cache block size of 128 bytes and then observe in hardware, for instance, that okay, so say the program uses this cache block and then it uses the next. Okay, why? Well, for instance, because it was going through an array. And what hardware often does, and the power machine does this, it is to detect that 2 consecutive cache blocks are accessed, and then it predicts that the program probably will need this one as well, so it fetches it on its own. That's an advantage to compare to fetching several cache blocks. I mean the amount of data that corresponds to several cache blocks. Since if the program doesn't use this, then it was a waste of time to fetch them. Okay, and there is another concern as well now that the world we live in consists of parallel programs. And that is, this is just to the end of this course, and just point out something that you should think about when deciding on, I mean, that is relevant for deciding a cache block size. So say we have an array in memory, and we have one thread writes to this part. So I mean, if we assume we have a parallel program and one thread writes here, say thread 1, okay, and then another thread writes here. And if this is all in the same cache block, then where should the cache block be? Well, if we have a sequential computer with only one support for only one concurrent hardware thread, then it will go to the cache that we have already seen, so it doesn't matter. But if thread 1 and thread 2 runs on different cores, then the hardware will make sure that this cache block is only valid in one of the cores at the same time. And what I'm coming to now is that if we have a too large cache block, then there is a bigger risk that one thread will destroy a cache block for another thread that they just happen to share, but actually not using the same data. So therefore, using a cache block size of several hundred in a parallel computer or multi-core computer is usually a bad idea. But if you want to learn more about this, then you should take this course. It's given next time in 2021, LP1. There you will learn a lot about cache memories and what actually happens when one thread writes to data. When will that data be visible to other threads? Okay, for instance, and many more things. How to divide a program so that they don't destroy each other's caches too much. Okay, but that's a different story, and I will not ask in this course about anything that is related to multi-course or multi-threaded program. That is all in this course instead. So you can view this course as a continuation of this course, but there is a difference. This course is not focused exclusively on C. Instead, we have several different programming languages, and last year it was Java, C, Scala, and Rust, and C++, and the goal was to solve a similar problem in all these languages and see which one is most convenient to do it in. Whether it will be the same languages next time, that's not sure, but at least this, well, and C++.